After learning prompt chaining for sequential workflows and routing for dynamic decision making, the parallelization pattern addresses tasks that contain multiple independent subtasks. Instead of executing them one after another, this pattern allows subtasks to run simultaneously, improving efficiency and performance in complex agentic systems. Parallelization means running multiple components like LLM calls, tools, or sub-agents concurrently rather than sequentially. By executing independent tasks at the same time, it reduces overall execution time for workflows that can be broken into separate, non-dependent parts. The concept of parallelization becomes clearest when we look at how a research agent handles a complex task compared to the traditional sequential approach. In the sequential workflow, the agent must complete each step entirely before moving to the next. So imagine an agent tasked with researching and summarizing a topic using two distinct sources, A and B. The process unfolds linearly. First, the agent must make first search for source A. This could involve querying a database or an external API, a task that introduces latency or waiting time. Second, only once source A is found does the agent proceed to summarize source A. Next, it starts the entire cycle over search for source B. Again, it waits for the result. And then it summarizes source B, and finally all four distinct steps are complete. The agent can synthesize a final answer for summaries A and B. The total time taken is the sum of the time for all five steps. If the search steps are time consuming, the entire process slows down considerably, like a single queue waiting for every individual action to finish. While we consider the parallel approach, the parallelization pattern is applied by identifying subtasks that are independent, meaning the search for source B doesn't need the summary for source A to begin. So using the same research task, the parallel approach optimizes execution. First, the concurrent execution. The agent initiates search for source A and search for source B simultaneously. Since these are independent lookups, they run in parallel, effectively cutting the waiting time for the search phase down to the duration of the longest search. Next is concurrent processing. Once both searches are complete, or as soon as individual search is complete, the agent simultaneously starts the summarize source A and summarize source B task. These independent LLM operations run at the same time. And the third is sequential synthesis. The final step, which is synthesize a final answer from summaries A and B, must remain sequential because it requires the result or summaries A and B from the previous parallel step. So by executing the independent search and summarization task concurrently, the parallel approach drastically reduces the overall execution time while still producing the exact same high quality final result. This optimization is crucial for building responsive and effective systems, especially those frequently interacting with external services that introduces latency. Like I said, the parallel approach reduces total execution time by performing independent tasks at the same time while producing the same final result. Parallelization involves identifying independent parts of the workflow that don't rely on each other and executing them simultaneously. This is especially useful when interacting with external services like API or database, where latency can slow sequential execution. And implementing parallelization typically uses asynchronous operations, multi-threading, or multi-processing, and modern agentic frameworks are built to design or built to work implementing parallel steps straightforward. The parallelization pattern is vital for improving the efficiency and responsiveness of agentic system, especially when dealing with tasks that involve independent lookups, computations, or interactions with external services. It's a key technique for optimizing the performance of complex agents. Now, when we talk about practical applications and use case of parallelization optimizes agents' performance by executing independent tasks concurrently across various domains. Power of parallelization is best demonstrated in real-world agent use cases, particularly where multiple independent information sources or analysis methods are required. First, information gathering and research. So imagine an agent tasked with providing a comprehensive profile on a specific company. A sequential agent would be painfully slow. First, search news, then wait, then pull stock data, then wait, and so on. While the parallelization pattern transforms this process. So the basic use case is researching a company. The agent simultaneously launches four distinct independent subtasks. The first is search news articles, maybe it calls an external news API. Second is the pull stock data, maybe it calls a financial API. The third is check social media, maybe it calls a platform API. And fourth is the query the company database, maybe it calls an internal service. Since the result of checking social media do not affect the stock data retrieval, these tasks run concurrently. This allows the agent to collect comprehensive information much faster, reducing the overall latency from four separate time-consuming waits down to the time of single longest task. The second is data processing and analysis. Parallelization is also a game changer when performing multiple complex or multifaceted analysis on a single dataset, such as large volumes of customer feedback. Consider a use case analyzing customer feedback. So, a sequential approach would run one analysis after another. A parallel agent is far more efficient, executing several types of analysis at once. The first can be sentiment analysis, where the agent can analyze whether the feedback is positive or negative. The second can be keyword extraction. The third can be categorization, maybe related to billing, service, or product. And the fourth can be urgent issue identification, uh, maybe identifying terms like bug or down or some other high priority terms. And by running these tasks in parallel, the agent quickly processes the data through multiple analytical lenses. This provides a multifaceted analysis quickly, enabling faster choice making, such as immediately routing urgent issues while compiling general trends. We can consider a multi API or tool integration or travel planning use case. So imagine a travel planning agent. To create a complete itinerary, the agent must interact with several external booking and information services. The parallel tasks, the agent doesn't check flights, then wait, then checks hotel, then wait. Instead, it concurrently calls the API for flights, hotel, local events, and restaurants. And by running these independent external lookups simultaneously, the agent presents a complete travel plan much faster than a sequential system would. Next would be content generation with multiple components or maybe marketing email. So for a marketing email agent, the final output is a composite of several distinct creative elements. The parallel task here, the agent executes independent generative task at once. Generate the subject line, draft the email body, find a relevant image, and create the call to action button. So this concurrency allows the agent to assemble the complete content efficiently, significantly accelerating the production pipeline compared to drafting each piece one after the other. Another use case can be validation and verification of user input. So when an agent needs to confirm the quality of submitted user input, it often involves multiple checks that don't depend on each other. So the parallel task here can be the agent simultaneously runs check for the validity of the email format, phone number, address structure, and scans for the input for profanity and or inappropriate content. So by performing these checks in parallel, allows the agent to provide faster feedback on input validity, improving the social media experience. And we can also consider multi-options generation or maybe generative creative text. So when an agent is tasked with generating optimal creative options like headlines, it benefits from producing multiple variations instantly. So the agent instructs the LLM to produce multiple headline or variations simultaneously instead of generating one, evaluating it, and then generating the next. So this allows the agent to quickly compare and select the best option, drastically cutting down on iteration time. So in conclusion, parallelization is a key optimization pattern in agentic systems, enabling developers to build highly responsive, efficient, and scalable applications by executing independent tasks concurrently. So in this video, we talked about parallelization. I'm going to end the video now and I'll see you in the next one.